Okay, welcome back. So now let's compute the pitching moment respect to the leading edge. So again, because if we kind of compute the pitching moment, if let's say we use sort of the normal forces, basically the pressure difference, the lower pressure is higher than the upper pressure. So you see, this is actually making the airfoil goes pitching down. So this will be a negative sign over there. And if we're trying to compute the pitching moment, of course we will also need to compute the arm, which is x over there. So then this is the formula for you to compute the pitching moment, and you're just integrating over all. All you need to do is just integrating over 0 to c, because this is where the airfoil is. Is basically what you're going to do is you kind of compute the total aerodynamic moment on the airfoil respect to the leading edge. So now, because we again, in terms of computing the integrations, we were just converting everything into theta space. The x can be converted into theta space by using this formula expression here, and the delta px is actually is rho u infinity times the gamma x, and gamma x there's a expression for gamma theta, so we just use directly here, and the dx is just you can rewrite them in terms of d theta. Okay, so for this long expression over there, I just rearrange it and just try to compute, arrange everything, and we end up with this integral, which basically tells us the answer is basically pi over 2, and this is the final result. It looks like minus pi over 4 times rho times u infinity square times c square times alpha. So this is a moment. If I want to compute the dimensionless quantity for pitching moment, that would be dividing the 1 over 2 rho u infinity square times c square. Okay, not just times c, but times c square. Because for pitching moment, we were computing the moment, there has to be another sort of length unit over there. Okay, so if you do that, and you use the expression to divide these nominator, you will end up with this. You end up with this minus pi over 2 alpha. So if I try to find the relation between them, between the lift coefficient and the pitching coefficient, I can actually find out that this is actually expression. The relation between them is actually the lift coefficient divided by minus 4 is the pitching moment. Okay. So that kind of tells you that the pitching moment is usually gonna pitching down for symmetric airfoil, right? Because the lift coefficient is positive. It's in respect to the leading edge. Okay, good. So now let's compute the center of pressure. So once we have the moment with respect to the leading edge, we can just use a very simple expression to compute the center of pressure. So in order to compute the center of pressure, it's just, the center of pressure is just the minus moment with respect to the leading edge divided by the sort of normal forces, actually. But here, since we have we consider things like small angle of attack, so it's just lift force. Then you can actually plug in the expressions to actually see, you see what it is. It's actually give you the center of pressure is actually at the quarter chord. So basically 25% of the chord length. You can actually somehow see this when you actually deriving the relationship between their non-dimensionless parameters here. You see a factor of minus 1 over 4, and actually this is actually related to a quarter chord length locations as the location of center of pressure. Okay, so as you can see, the center of pressure meaning is actually independent of alpha, as you can see here. because the center of pressure as the kind of expression I derive here is valid for sort of a small range of alpha, but the alpha can change. But you see the center of pressure didn't change. That means the center of pressure is independent of angle of attack. And the moment on the center of pressure, of course, is zero by definition. That means the aerodynamic center should be the same as the center of pressure for the symmetric airfoil. Why? Because the definition for aerodynamic center is that if you compute the moment respected to the aerodynamic center, the moment should not change with respect to angle of attack. There should be a constant moment here, which exactly is the case here, because the center of pressure, the moment is zero always, and the center of pressure didn't change with the angle of attack for the symmetric airfoil, at least from the thin airfoil theory. Therefore, we have this nice conclusion that aerodynamic center is the same as the center of pressure for symmetric airfoil. Okay, so as a summary for the conclusion for symmetric thin airfoil is that we have the lift coefficient as the 2 pi times alpha. Alpha is the angle of attack. And once we have the lift coefficient, the moment coefficient respect to the leading edge will be the lift coefficient divided by -4. And the moment respected to the quarter length of the cord, a quarter cord, 25% of the cord length, if you compute the moment over there, it's going to be 0. So the momentum coefficient of that will be 0 as well. And the center of pressure, as well as the aerodynamic center for symmetric airfoil, would be at the 25% of the cord length if you compute it from the leading edge. Okay, so it will be C divided by 4. Good. So how good is this theory? So here is the airfoil data for NACA 0012. If you see NACA 00, if it starts with 00, you know it's a symmetric airfoil for sure. Okay. So you see for this case here, it's actually pretty good. So if you're trying to compute the slope of this line, you can convince yourself. You can just try to convince yourself. You can just go over there, for example, and try to compute the delta CL divided by delta alpha. Now the alpha here is the degree. So you will see that it's approximately 2 pi. It's approximately 6.28. Okay, so it's actually pretty good in terms of the lift coefficient. For the momentum, actually this line here is actually computing the moment respect to the 25%. You see, C over 4. It's 25% of the cord length. And actually also pretty good. It's basically tells you there should be zero moment there, and it should not change with the angle of attack too much. As you can see, when you have a large angle of attack, things definitely goes south. It's no longer a straight line, for example, for the lift coefficient starts to go down, and even the moment starts to change. It's not going to be 0 anymore. So these cases are, it's because they are not valid because the assumption for thin airfoil theory breaks down for those cases, because if you are like 16 degrees, it's sort of no longer in the range of thin airfoil theory, because it's kind of assumed the angle of attack is smaller than 12 degrees, things like that. For the left plot over there, forget about it, because the potential flow theory can't tell you anything about drag. So basically, just there's no drag for. We cannot comment anything on the drag because this is our potential flow theory. There's no drag in potential flow. Okay, so now let's switch gear to apply this to cambered airfoil. A cambered airfoil meaning that now the interesting slope, the camber line slope, The camber line, again, it's the average between the upper surface and the lower surface. So the average profile between upper surface and lower surface. So the slope for this one will not be 0. And now it will be more it will be more interesting to apply these equations here. So so now the gamma theta will have a much more complicated expressions. Okay, so for the sectional lift, again, it's going to be just the pressure difference, and we in terms of the pressure px, it's going to just be the rho u infinity times the gamma x. The gamma x, you better express the gamma x as a function of as a function of theta, because here it's easier to integrate everything in theta, at least for the airfoil theory. So you can actually plug in the sine theta inside and try to compute all the things inside over here, and you can actually convince yourself that for the sectional lift, only the first two coefficient A matters. Only A0 and A1 matters. Everything else will cancel out. They actually use the orthogonal conditions for trigonometric theories, and I've uploaded a handwritten notes on that thing in LMS. Please check them out if you find this line, for example, this line to this line here is confusing. Okay, good. So if we want to compute the non-dimensional lift, we just compute the lift coefficient CL, and if we just plug the expression inside, we just get going to be a nice expression. It's going to just be related to A0 and A0, and A0, remember, it's actually related to alpha, angle of attack. This alpha that's where alpha comes in. Alpha comes in through A0. So if you kind of write down expression like that, you will see the alpha is kind of separated with a long integral term over there. That integral term over there, that integration will call it minus alpha L equals to 0. Okay, what does that mean? That means if alpha is if angle of attack reaches this sort of zero lift angle of attack, okay, then literally just means the lift coefficient will be 0. Okay, so typically this will be a negative number for a positive camber airfoil, because you would have to go to negative angle of attack in order to balance the force on the airfoil such that it won't create any lift. Okay, but still, we have the same relation, sort of the same slope for the slope for the lift coefficient versus the alpha. Okay, even for cambered thin airfoil, this still holds. Great. So how about the pitching moment here with respect to the leading edge? So I'm not going to show the result. I'm not going to sort of derive the result here. It's just tedious calculus exercises. And basically, you see the result involving the first three terms, A0, A1, and A2. No more other terms. No matter how complicated your airfoil is, how fancy the camber line slope looks like, no, there's only three terms come out of this, and you just need to compute those three terms. That's it. Okay. So for the center of pressure, again, we use the formula as we did before. So for the center of pressure, that means if we take the moment on that point, there will be zero moment at all. Okay, so if we just plug in this expression over there, let's try to compute the center of pressure. We can actually see a lot of things canceled out, and we end up with this nice expression that only involves the coefficient of those capital A coefficient in the gamma theta expansions. So basically, it tells us it's just if I kind of wanted to define a non-dimensional number for the center of pressure, that's just going to be center of pressure divide the C over there, is actually related to the difference between A1 and A2. And also a nice thing about it is, you see, the center of pressure here it actually will change with alpha. For this case here, for the general cambered airfoil case, it will change with alpha because the lift coefficient is right here. Lift coefficient changes with alpha. Therefore, center of pressure will change with alpha as well. But for symmetric airfoils, capital A1 will equals to capital A2, so this term canceled out. But here we have a cambered airfoil, which is a more general case. The center of pressure will change with respect to the angle of attack, and it will be no longer C/4. Okay, good. So how about aerodynamic center? The definition for aerodynamic center is that if I change angle, if I take a moment with respect to that point, and I change angle my angle of attack, my moment with respect to that point won't change. Okay, so now let's see how can we actually compute the angle of attack, the aerodynamic center. Okay, so let's first try to compute the moment around C/4 because I think this will probably be easier. So let's compute the moment with respect to the quarter chord length over there. So as you can see, if I plug everything inside, I actually get a sort of the thing, capital A naught canceled out. The capital A naught is where the angle of attack enters the relation. Therefore, but the A1 and A2, they are only determined by the shape of the camber line. It has nothing to do with angle of attack. Therefore, if I compute the moment with respect to a location C/4, I end up with a moment that is independent of A naught, which means it's independent of the angle of attack. Therefore, it means the one we just choose, C/4, is an aerodynamic center. Okay, great. So it's also a very important conclusion that for any kind of thin airfoil, the quarter chord is basically the aerodynamic center. Okay, good. So here's a summary. We have the lift coefficient as a function of alpha. Basically, the slope will be 2 pi, but there will be a sort of intercept or sort of a bias. The bias is usually what we call zero lift angle of attack. Okay. Okay, so here's the expression for the zero lift angle of attack. For the center of pressures, unfortunately, it will change with angle of attack. And this is the expression over there, and it's only the reason why it's changed with angle of attack is because the dependency on CL. The CL is a function of alpha. Okay. For the aerodynamic center for thin airfoil, it's just going to be C/4. It won't change with angle of attack. It's just C/4. It's just 20 plus 5% of the chord length if you're starting from the leading edge. Okay. And the moment with respect to the aerodynamic center for camber thin airfoil will just be pi/4 times the A1 minus A2. Okay. Good. So next I will talk about 2 examples, and let's take a break here, and